Hey everyone, in this short video, we'll be covering a very useful limit theorem that involves sequences. Now this theorem is covered in Math 2111 or 2011, but it's very useful in general, and that's why it will be covered in this video today. Now first, I want to give you some motivation as to why this theorem is very useful. Now first, we know how to determine whether a limit of a function exists. For example, well, for very simple functions actually. So for example, sin x has no limit as x goes to infinity, sin x on x goes to 1 as x goes to 0, and other similar things like that. But what about limits involving many variables? And for example, does this limit exist? The limit of xy all over x squared plus y squared as xy goes to 0, 0. Well, our useful limit theorem can give us the answer. This theorem takes in two assumptions. First, f has to be a function from omega to Rn, where omega has to be a subset of Rm. Also, A has to be in the closure of omega, which means omega itself plus its boundary, and also B must be in Rn. Now this is the result. Fx goes to B as x goes to A, if and only if f of xk goes to B as k goes to infinity, for every sequence xk from k equals 1 to infinity contained in omega, with xk going to A as k going to infinity. Now this is quite a lot to unpack, but all this means is that if we approach A with two different sequences, but approach different function values via these sequences, then the limit does not exist. Now this is only useful for proving that a limit does not exist. This is because if we wanted to prove that a limit did exist using this theorem, we would have to show something for every single sequence that goes to A as k goes to infinity. And that's not an easy thing to do. To demonstrate this theorem, let's do some questions together. So, first question, show that the following limit does not exist. The limit of xy on x squared plus y squared as xy goes to 0, 0. Now, in terms of our theorem, we have f of xy equals xy on x squared plus y squared, and f goes from omega to r, where omega is r2 except the 0 vector. We omit the 0 vector for obvious reasons because the denominator can't be 0. Also, A has to be 0, 0, according to this theorem, which is just this part. Now, continuing on. The first step we have to take is to find two sequences that go to 0, 0. Now, for the sake of example, I'll be defining these two sequences, but when you do actual questions, you will have to come up with these sequences yourself. Now, let's define AK equals, well, not equals. Let's define AK with AK equals 1 on K, 1 on K, and another sequence, BK, with BK equals minus 1 on K, 1 on K. Okay, so the next step, well actually before that, we just have to do a brief check that these sequences actually go to 0, 0 as K goes to infinity, but it's very clear in this example. Now the next step is to take the function values of these sequences. So first, what is f of ak? Well, f of ak would be just f of 1 on k, 1 on k, which is 1 on k times 1 on k all over 1 on k squared plus 1 on k squared, which is 1 on k squared on 2 on k squared, which is 1 on 2. And as k goes to infinity, this just goes to half. As k goes to infinity. We do the same thing for bk. So also, f of bk equals f of minus 1 on k, 1 on k, equals minus 1 on k times 1 on k, all over 1 on k squared plus 1 on k squared, which is minus 1 on k squared on 2 on k squared, which is minus half. And this obviously goes to minus half as k goes to infinity. Now, if you notice here, these two values, fak and fbk, they approach different values, half and minus half as k goes to infinity. And so this means that by our useful limit theorem, that the original limit does not exist. So therefore, since the limit of k goes to infinity of fak is not equal to the limit of k goes to infinity of f of bk, the original limit does not exist. And in summary, this is because we have two sequences that go to 0, 0 as k goes to infinity. They both go to 0, 0, but their function values, fak and fbk, they don't approach the same value as k goes to infinity. It's like saying you're approaching the same point in two different directions, but you don't end up at the same point. Okay, let's try another example. So another question. Show that the following limit does not exist. This is limit of xy squared over x squared plus y to the 4 with as xy goes to 0, 0. So similar to before, we first need to determine two sequences that go to 0, 0. So let's define, for the sake of example, AK, define the sequence AK by AK equals 1 on k squared, 1 on k, and say BK by, say, BK equals minus 1 on k squared, 1 on k. Now, we do the same thing as before. We find the f of ak, so f of ak equals f of 1 on k squared, 1 on k, which is 1 on k squared times 1 on k squared on 1 on k to the 4 plus 1 on k to the 4. And this is just 1 on k to the 4 over 2 on k to the 4, which is a half. This goes to half as k goes to infinity. Same thing for f of bk. So and f of bk equals f of minus 1 on k squared, 1 on k, which is minus 1 on k squared times 1 on k squared, all over 1 on k4, k to the 4 plus 1 on k to the 4, which is minus 1 on k to the 4, 2 on k to the 4, which is minus half, which goes to minus half as k goes to infinity. It's a similar thing as before. These function values of two sequences that approach 0, 0, they're different. So, therefore, since limit of k goes to infinity or f of ak is not equal to the limit of k going to infinity of f of bk, the original limit does not exist. Again, we have two sequences that both go to 0, 0 as k goes to infinity. They go to the same point as k goes to infinity, but their function values don't approach the same thing as k goes to infinity. And that's why the original limit does not exist. Thanks for watching this video. Hope it helped.